It's a ratio, yes. What makes something a rational function? It'll look like a ratio. It'll look like a fraction. So when I think rational, I think the variable's in the denominator. Variable, or like the input variable, is in the denominator of a fraction. Okay. Parent function. So remember, parent function just refers to like the most basic one you can graph. What do we remember about the linear parent function? Bless you. Linear parent function is y equals x, just x. What do we remember about the quadratic parent function? Y equals x squared. Good. It's always just the most basic one we can graph. Our parent function for a rational function is the function y equals 1 over x. 1 over x. This is the most basic one we can graph. It has no transformation, no left, right, up, downs. We're going to make ourselves a little chart, a little table to graph it. So I'm going to pick some negative numbers. I'm going to pick 0 and some positive numbers so that we get a good idea what this graph looks like plugged in. So again, if we're making ourselves a table to graph, we're plugging it in for the denominator over here. So if I plug in 1 divided by -3, well, that's just -1/3. 1 divided by -2 would be -1/2. Very good. 1 divided by -1. -1. 1 divided by 0. Undefined, right? Undefined. 1 divided by 1, 1. 1 divided by 2, 1/2. And then 1 divided by 3 is just 1/2. Or excuse me, 1/3. Okay, so we've got ourselves 7 points that we can graph. Okay, so looking at the first one, we're graphing -3, -1/3. -3, and then -1/3 is kind of left 3 and then down a third. And then we have -2, -1/2. Okay. -1, -1. And then we have 0 undefined, so we're not going to plot a point for that one. And then we have 1, 1. 2, 1/2. And then 3, 1/3. And I know this kind of doesn't give you a great idea of what it looks like. Bless you. I'm going to plug in a little fraction point just to kind of help us understand what this graph is doing. If I plug in the fraction 1/2, what's 1 divided by 1/2? 2. So I would have a point at 1/2, 2 up here. So that's kind of giving us a better idea of what it's doing. If I plugged in 1/3, what would I get? 3. 3. So 1/3, we're at 3. And is there anything I can plug in where I'm going to actually get 0 right here? No, you're just going to get, it's just going to go higher and higher and higher. So as it goes towards 0, it's just going to continue up this way. As it goes towards infinity to the right, same kind of situation is happening. This one has 2 asymptotes. It has a vertical asymptote and a horizontal asymptote. Same thing happens on the other side. Each of these little parts of the graph is called a branch. So this rational function has 2 branches and 2 asymptotes. And again, this is just the parent function. They can move left, right, up, down. That's not mine. Interesting. Again, I had a lost one, but I found it today. All thanks to Liam, guys. Okay, how would we describe the shape of this? Anyone know what the name of this shape is? Okay, so U-shaped graph is called a what? Parabola, right. This one that has 2 branches, this one's actually called a hyperbola. That is its technical name, hyperbola. Okay, it has 2 branches. And again, this is just the most basic one. There are some rational functions that have 3 branches, depending on the number of asymptotes. There's some that have just 1 branch, and they look like like a bell curve almost. What features does it have? It has 2 asymptotes, an x asymptote, or excuse me, an vertical asymptote and a horizontal asymptote. Vertical and horizontal asymptote. What features does it not have? It doesn't have an x and a y-intercept. Now, that doesn't mean all of them don't have that. It's just the parent function does not have an x-intercept or a y-intercept. X-intercept, y-intercept. We're going to do a basic transformation of a parent function just to kind of see how it moves. Most of what we do are not these basic ones. These basic ones are kind of boring because they do very little movement. So our transformation form of the parent function would be y equals 1 over x minus h plus k. Those hk's, they never go away. Is h a horizontal or vertical translation?
Horizontal.
H is the horizontal one, right? This one is the one that causes it to move left or right. So left, right. The K is the vertical translation, just like it always is. This is the one that moves up or down. And which one moves backwards from what our brain wants to think? The horizontal one, the X one, right? Okay. So when I look at this graph, it has 2 transformations listed. It has this -1, that's my H, and this +2, that's my K. The top number is technically considered your A value, and the top number, can make it look slightly different, whether it's reflected or skinnier or narrower, but we mainly focus in on the H and K right here. The H is a -1, which means which way is this graph going to move? 1 to the right, 1 unit right. Okay. Our K is a +2, which means which way is it going to move? Up 2. Okay. And specifically what's important about this is it also moves the asymptotes. Both of these movements include the asymptotes moving. Moves asymptote. Okay. So I'm going to start by taking my vertical asymptote. My vertical asymptote is normally at x equals 0, and it's going to move 1 unit to the right. Okay, so if it's normally at 0 and it moves 1 unit to the right, now it's at 1. Okay, and then we'll have our horizontal asymptote, which is also at 0, but this one's going to move which way? Up 2. Very good. Okay, now our function does still have 2 branches. Our job is to just figure out a point on each branch. So I want to plug in numbers that are over here to the right of 1, and I want to plug in a number that's to the left of 1 so that I get at least 1 point per branch. You don't need more than that unless you really like plugging in points. 1 point per branch. Let's pick some points to plug in for x and y. On the right-hand side of +1, what x value would y'all like to plug in? 2 sounds great. Okay, so if I plug in 2 for x, I'm going to have 1 over 2 minus 1 plus 2. 2 minus 1 would be 1, so what's 1 over 1? And then if I add 2, I get 3. So I'm going to have a point at 2, 3. 1, 2, 1, 2, 3. Okay, and then I need to also plug in a point that's on this left side of +1. 0 sounds great. So we'll have 1 over 0 minus 1 plus 2. So let me see, that would be 1 over -1, which is -1. And what's -1 plus 2? 1. So I'll have a point at 0, 1. Okay, and now we know what the general shape of this graph looks like. Okay? it's going to have a branch that kind of curves towards the asymptotes in both directions, curves towards the asymptotes on this side. Sometimes the branches swap depending on if this number up top is negative, like they'll swap and be here and here. And you'll just find that whenever you find your points. You'll be like, oh, okay, it's on the other side on this one. So I don't need to plug in more points now that we know what the general shape is. But what I'm going to do is I'm going to take this one point that I grabbed and I'm going to cause it to go closer towards the horizontal asymptote as it goes towards infinity. And then it's going to go up towards our vertical asymptote. And same thing for the other one point that we found. We know what the general shape looks like now. So it's just going to curve towards the horizontal asymptote as it goes towards the left. And as it goes towards the right, it's going to follow down that vertical asymptote. It does say for us to find the domain and range. Domain and range. Let's do the domain and range in set notation. Which was set notation?
The one with the little
The one with the squiggly brackets, right. So I'm going to open a squiggly bracket. And the domain is every single number except for which number? 1. Every single x except for 1. So here's how we're going to write that for our domain. Okay, I'm going to say x is a real number, meaning it could be any number from negative to positive infinity. So I'm going to say x is a real number. This little symbol here, it looks like a curved E. It just means in the set of real numbers. X is in the set of real numbers. Except for which number again, Paul? 1. So then next to that, we're going to say x is not 1. Our range is similar, except range is y's. The range is also all real numbers, except for which y? 2. Very good. 2 is excluded, but every other number is included. So I'm going to say y is a real number. That's just the technical notation way, except for 2. I know it seems like a pain to write the domain and range like this, like, like, why can't we just say negative infinity to 1, 1 to infinity? But whenever we start getting more asymptotes, it gets to be a really big pain in the butt to use interval notation. So I just start training people on just do set notation. It's a real number except for this one. It's a real number except for this. All right, dig your whiteboards out of your desk real quick. Whiteboards out of your desk real quick. Grab a marker. All right, I want you to write me a rational function equation that has been translated left 5 and down 3. It's been translated left 5 and down 3. Just keep the a value 1 so you don't need to switch up the top number. A rational function equation that's moved left 5. Good. Technically you forgot the y equals, but left 5 and down 3. Boom, 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 boom. Oh, Liam, I can't see yours. Liam, left 5. Left 5.
Oh, that's fine.
The table looks good in the back. That looks good. Thorn, you write so tiny. Good, good, good. Good, good. All right, erase. Let's do another one. Look at y'all erasing just specific parts. Good job.
Boy, that's fine.
Okay, write me a rational function that's moved right 4 and up 1. It's translated right 4 and up 1. Boom, 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 boom. Boom, 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 boom. Yours is left 4, right 4. Boom, boom, boom. All right, you can put the whiteboards to the side for now. All right, see how easy basic ones are? Basic ones just move, yeah, that's. All right, let's look at the general form of a rational function now on the back side. General form. Okay, all rational functions can be written in the general form of y equals p of x over q of x. And I know that looks weird, but p of x and q of x are both polynomials. So a polynomial can be anything as simple as like what looks like a linear function, or it can be even higher. It can be a quadratic, it can be a cubic function. Obviously, we're going to start very small today. For today, we're starting with just something that looks like a linear function over a linear function. So our general form would be y equals ax plus b over cx plus d. And so it just looks like a little linear function over linear function, but it is still rational. Why? Why is it still rational? It's a ratio, more specific than it's a ratio. There's a what? No, what makes it rational? X is on the bottom. That's what makes it rational. Very good. Okay. To find the vertical asymptote, we no longer have that cute little HK where we can just be like, oh, it's this number and this number. To find the vertical asymptote, though, the vertical asymptote is where your denominator is going to equal 0. Because basically that would give you a fraction with a 0 on the bottom, so it would be undefined there. So we're going to set the denominator equal to 0 and then solve it. Set denominator equal to 0 and solve. Horizontal asymptote. The horizontal asymptotes, they do change. We'll look at that on Wednesday this week. Other possibilities for horizontal asymptotes. But for today, when we're dealing with just a linear function over a linear function, our horizontal asymptote is going to be y equals, because it's a horizontal line, and it's just going to be the ratio of these two leading coefficients on the x values. So y equals a over c. It's just the ratio of the leading coefficients. And again, later on this week, we'll look at more challenging ones where the horizontal asymptotes might change and be something different. But for today, it's just a over c. All right, we're going to graph each of these rational functions and find their key features. Okay, I can see this one is in the general form. What is the leading coefficient on the top x? -1. What's the leading coefficient on the bottom? 1. That's going to help me. Okay, to find my vertical asymptote, to do that, we're going to take the denominator, we're going to set it equal to 0, and then solve. So for my vertical asymptote, I'm going to take the denominator, set it equal to 0, and I'm going to solve this to get what? 3. Now you add 3 to both sides, x equals 3. So that's where my vertical asymptote is. My horizontal asymptote is going to be the ratio of these two leading coefficients. -1 over 1 would simplify to just -1. And my x-intercept. How do you find the x-intercept of any function in the whole entire world? Set y equals 0. For my x-intercept, that's when y equals 0. I'm going to say 0 equals -x plus 2 over x minus 3. How would I solve this for x? Yep, we'll multiply by the denominator, which is nice because it gets it to kind of just cancel out, because when you multiply by 0, it goes away. So then I get 0 equals -x plus 2. Or I could do it in one step. I add x. Makes it one step. So we get x equals 2. As a point, what would that be? Because the x-intercept is a point. 2, 0. Very good. 2, 0. Good. How do I find the y-intercept of any function? That x equals 0. Good. Which basically means I get to plug in 0 for this one. So I'll have y equals negative 0 plus 2 over 0 minus 3. What does that simplify to?
Negative 2 over 3.
2 over negative 3, which is just negative 2/3. As an ordered pair, though, how would I write that? 0, negative 2/3. So this gives us a lot to graph, and then we can always find more points if needed, make a tiny little table to find extra points if needed, but I'm going to start by graphing the two asymptotes that I found. My first asymptote was x equals 3. This is the vertical one. Okay, and then I have a horizontal asymptote at y equals negative 1. Okay, and I'm going to graph the 2 points that I found. Also, I found an x-intercept at 2, 0, and I found a y-intercept at 0, negative 2/3. So if you look at these 2 points are on the same branch. Okay? And remember, in order to graph a rational function, I want at least 1 point per branch. Okay? Both of these are on the same branch, so I can draw this branch. As it continues towards 3, it's going to go up. As it continues down and left, it's going to go closer to the horizontal asymptote. But I do still need to find one more point that's on the other branch. I know it's going to be diagonal, but I need one more point.
Like mirrors.
Not necessarily. On these easier ones, they might be, but not always. Extra point. Which means I need to plug in something to the right of positive 3. 4 sounds great. Okay, so I'm going to plug this in for my x to find a y. So we'll have negative 4 plus 2 on the top, and on the bottom we'll have 4 minus 3. What does that create? Negative 2 over 1, which is just negative 2. So I'll have a point at 4, negative 2, which, as I said, Danny, it is often a mirror on these easy ones, but not necessarily when we get to harder ones. 4, negative 2, and I only need that 1 point. That 1 point is enough to know what it looks like, then I'm just going to kind of follow the asymptotes. As it goes towards 3, it's going to go downwards and follow that vertical asymptote. As it goes to the right, it's going to just get closer to that horizontal asymptote. And then filling in our domain and range, we're going to look at, we know it's every single x and y except for just one particular one. So my domain is going to be every real number except for which x value? 3, right? 3 is the only number that's not in the domain. It goes left and right forever, except it skips over 3. So I'm going to say x is not 3. Okay, for our range is every single real number except for which one? Negative 1. Good job. Y is a real number except for negative 1.
Why is it? When we multiply the by x rows, why did it just cancel out?
Because you multiply it by 0. Yeah, 0 times anything is 0.
I mean, like on the we multiply.
They're diagonal, so they cancel.
Yeah.
Good question. All right, let's try one more of these that has all the features. Okay, I'm going to start by just identifying those leading coefficients. What's the top number leading coefficient? Negative 3. Good. What's the bottom number or the bottom leading coefficient? Negative 1. So we have a negative 3 over negative 1. Okay, how do I find the vertical asymptote again? Vertical asymptote. Make what equal 0? Make the denominator equal 0. Good. So for our vertical asymptote, we're going to take negative x minus 1. We'll set that equal to 0. Fastest way to solve this one is add x so that it just is on the other side and positive. Very nice. So we get negative 1 equals x. So what's my vertical asymptote at? Negative 1. And my horizontal asymptote. Horizontal asymptote is just the ratio of those two leading coefficients. So the top number is going to be negative 3. The bottom number will be negative 1, and that's going to simplify to y equals 3. X-intercept, how do we find that again? Set y equal to 0. Very good. We'll have 0 equals negative 3x plus 2 over negative x minus 1. Sean, to cancel that denominator, what are we going to do? Good. And what happens to it on the right-hand side? Cancel that. What happens to it on the left-hand side?
3x minus.
What's anything times 0? So negative x minus 1 times 0 will be 0. Kind of makes it a lot easier. It's nice that it turns to 0. And then that leaves me with negative 3x plus 2. Okay, then what? Yeah, at this point you can either, I'm going to add 3x. Doesn't really matter though. So 3x equals 2, which means x equals 2 over 3. Good. For the intercept, what would that look like as an ordered pair? 2/3, comma 0. Yep. Okay. Y-intercept. How do you find the y-intercept of any function? Very good. And this is the one we get to plug in 0 for x. So we'll get y equals negative 3 times 0 plus 2 over negative 0 minus 1. What does the numerator simplify to? 2. Yeah. What does the denominator simplify to? Negative 0 minus 1 simplifies to negative 1. And what's 2 divided by negative 1? Negative 2. Good. As a point, how would I write that? 0, negative 2. Very good. All right, I'm going to put all that on my graph, and that'll kind of give me an idea if I need any extra points. So we have a vertical asymptote at x equals negative 1. We've got a horizontal asymptote at y equals 3. Okay, I'm going to graph the two intercepts and then determine if I need to find any more points. My x-intercept, my x-axis is here. So my x-intercept is at 2/3, 0. And my y-intercept is at 0, negative 2. Are these points on the same branch or are they on different branches? They are on the same branch, right? So if they're on the same branch, I can draw this branch. I know what it's going to get closer to the asymptotes in each direction. But I want to find one more point that's on the other branch. So I'm going to find an extra point. Danny wants to plug in negative 2. Is that what you said? Why is negative 2 a good choice? Left. Yeah, it's on the left of negative 1. That's really your only goal, is to get your point on the left of negative 1. All right, that'll give me, let's see, negative 3 times negative 2 plus 2 over negative of negative 2 minus 1. Negative 3 times negative 2 would be 6, plus 2 is 8. On the bottom, we'll have 2 minus 1. That's nice. Negative 2, 8 then. All right, negative 2, 8. Now I see why I made a bigger graph on this one. I was like, why did I put a different coordinate plane on this one? Now I know why. Negative 2, 1, 2, 3, 4, 5, 6, 7, 8. And you only need 1 point because you know what the general shape of a branch looks like now. It just follows the asymptotes, gets closer and closer. All right, my domain. Domain is every single x except for which one? -1. So say x is not -1. My range is every single y except for which y? 3, because you have that asymptote there. So we'll say y is a real number, except y is not equal to 3.